For the next speaker, we're very happy to have Torres from UPenn, and he'll talk about reflection anomalies and meta content of M theory on local spin 7 spaces.
Hello. I was going to say, I want to thank the organizers for having me talk, and also for continuing to have this very nice virtual seminar, even though things seem to be opening up from the pandemic. So today I'm going to talk about M theory on spin 7 manifolds, and let me just discuss some of the general setting. So what I want to consider is a compactification of this form. Can you all see my mouse, by the way?
Yeah, we can see it.
Okay, so I consider something of this form where X8 is some non-compact spin 7 manifold, and I want to think about what are the dynamics of this 3D n is equal to 1 theory. I'll call cow t X8. Where throughout I'll consider X8 as a ALE fibration with partial blowups fibered over M4. And the reason why this is interesting is, well, it could have applications to condensed matter. These theories are generally very hard, so it sort of puts a lot of geometric engineering constructions to the test. And what makes it quite difficult is that there's no holomorphy, the superpotential, and no non-normalization theorem to help us out. And furthermore, the gauge coupling, so this is the gauge coupling defined in the UV, is of order mass. So therefore it's relevant and becomes strong in the IR, even for abelian gauge theories. So so it would be nice to study what possible structure you can extract from the IR. And one way to get some mileage is to assume that this theory is symmetric under reflections. So for one thing, the superpotential will be odd. So this restricts some of the perturbative corrections that you can get. But what we'll really look at today is the Hooft anomalies of this reflection. Namely, this reflection when it's mixed with gauge and gravity transformations. So in particular, the Hooft anomaly of reflection mixed with gravity amounts to the obstruction of placing this theory on an unorientable 3-manifold. And this 3-manifold unorientable, we're taking to mean pin plus structure because we're assuming M4 is oriented. In M theory, it can only be defined on 11 manifolds with a pin plus structure because the 11D Majorana fermion only has a pin plus representation, not pin minus. So, and for those of you who don't know the difference between pin plus means that this R1 squared is equal to 1, as opposed to pin minus, where this R1 squared would be equal to -1 to the fermion number. Okay, so the goal that I'll for today will be to compute these anomalies for a general class of these local models right here. So the plan will be to review some of the classical behaviors. So some of the name of the Vps equations from the 70 superring mills, and let's see, and extract basically the classical matter content. And then we'll look at how to define these reflection symmetries. So in defining these reflection symmetries in the 3D and seeing how they descend from the M theory and the 70 superring mills, this is a bit more non-trivial than you might expect. Determining the signs and everything on this project took a lot of time, so I'd like to show you guys. And then finally we'll study the observables that we can extract after quantum corrections and in the IR, namely these Hooft anomalies and some of their M theory interpretations. And we'll also look at an example, and then we'll finish with some conclusions. So M theory local models in general, you can think about an ALE fibration over a Riemann surface of a 3-manifold or a 4-manifold. We're going to study this today, but just to comment on these other cases, they correspond to local plug out threefolds, G2 and G2 manifolds, and these give these theories. Let's see. Yeah, and if you don't blow up at all, then you basically just get the 70 superring Mills compactified on this. The lower energy physics is approximated at 70 superring Mills compactified on one of these guys, and then gives you one of these theories. And you have to perform this topological twist, which I'm just writing the what it looks like in general. This is the holonomy group of the internal manifold over here. And note that I'm always picking a global gauge group that is simply connected. If you want to look at how you would choose your 70 superring Mills, which is naively just determined by a Lie algebra, and how to pick more general global structures, then I would look at this paper. A crucial part of the dictionary is that blowing up these ALE spaces along the fibers of this vibration corresponds to turning on these 70 superring Mills scalars. So this A runs from 1 to 3. So this omega over here represents hypercalar form, basically. These I's represent the different P1s or S2s that are part of the blowup. And also you can turn on a VEV for the gauge field. This will come from reducing the C field of M theory. In general, so this is the abelian data, or you can think of the maximal tori data. But you can also, in general, these VEVs A and phi can be non-commuting, namely Lie algebra valued. And these non-abelian VEVs are what many people call T-branes. So just to look at what the Vps equations are in each of these cases, so we'll be interested in this today. These are also known as the Pfaffer-Witten equations, or just a slight truncation of the Pfaffer-Witten equations. And to explain what's going on here, for the case when we have an M4, this phi, which started off life in 70 superring Mills as a triplet of 3 scalars into the S2R symmetry, turns into a 2 form, so a section of this of M4. And this product here basically amounts to a cross product of self-dual 2 forms. Yeah, so self-dual is denoted by this plus here. So the intuition is that there's at any point in the tangent space on M4, there's 3 linearly independent self-dual 2 forms you can pick, and you can define this cross product structure. Okay, and just to comment on the type 2A dual, if we were to look at just a background where phi is switched off, and for this group, then it would just, the manifold X8 would just look like this quotient of a bundle of right-handed spinors M4 mod Zn, and then this is the M theory case, and then the type 2A dual would look like n+1 d6 branes wrapping the co-associative 0 section of this guy right here. So this also motivates the product I discussed on the previous slide. Okay. So for today, we're going to study abelian local models. T-branes for these spin 7 equations is quite challenging. So we're going to be looking at Higgsing of this form, possibly with multiple U1s. And the Vps equations just simply become this. Technically, I should include an A right there if I want A to be a flat connection, but yeah, whatever. I'm mostly going to be turning A off as well. So we have generic singularity enhancement with along circles inside the M4. So that just corresponds to the 0 set of phi. So that's when locally the ALE space will enhance back to the parent gauge group over here. And mathematical result due to Perutz is that the number of 0 mode circles is equal to this thing mod 2. I should technically write it mod 2 right here. So that can be rewritten as this topological quantity, where this is the Euler characteristic and this is the signature. Furthermore, the homology of this collection of circles along the M4 is trivial unless we allow for singularities, which we will do later. So in this figure, if this set of circles is homologically trivial, that means, let's say this guy wraps one circle in one direction. This guy wraps a certain, by circle I mean cycle of M4. This one wraps a cycle in M4 in the opposite direction. And this one doesn't wrap a cycle M4. So this would be homologically trivial if that's the case to satisfy this. Okay, so just to study a model solution on RT times R3. So this T is not time. I'm basically setting M4 to be this. Basically you get two important types of solution. This phi SD, that's just the background Higgs field. I'll just find plus plus minus to denote basically, you can think of it as a Morse index defined this way. So I should put a sculpture 1 here. So I have a decomposition of this self-till2 form in terms of a 1 form, and which is a 1 form along the R3. And this 1 form can be written, in order to get this formula up here, can be written as d of a function with a positive Morse index. So I can switch back and forth. So in G2 local models, which G2 would just look like I'm taking R3, there's an important distinction between plus plus minus and minus minus plus. But in the case of spin 7, you can exchange this t coordinate to go to minus t, and you can exchange this plus these positive and negative Morse functions, illustrated by this diagram. So this will be important later. Basically in the G2 case, so you're expecting 40n is equal to 1 matter. The plus plus minus is correspond to chiral modes, and minus minus plus will correspond to anti-chiral modes. So that's the importance. And this is just commenting that I'm generally taking some sort of singularities in the Vps equation. So some sort of flavor branes are intersecting the system. So under this Higgsing, okay, let's look at what the matter content we get. So we study the matter content by looking at perturbations around the Vps, like this. So a perturbation around big A corresponds to this little a, and perturbation on phi corresponds to this far phi. And these are both scalars in the 3D space-time, but they have some sort of representation along M4. So this is a vector along M4, a self-till2 form along M4. And so what do we get after doing this? Then we get a n is equal to 1 vector multiplet in the gauge group. So that corresponds to a 3D vector in adjoint Majorana. Adjoint scalar multiplets kind of by this quantity here. Uncharged scalar multiplets, so just some singlets also counted by this guy. And also, this is the crucial part, localized matter counted by solutions to this equation. And we also have a superpotential by expanding out this. And I should also comment, I should also comment that in 3D n is equal to 1 language, a scalar multiplet means a Majorana, a 3D Majorana fermion, and a real scalar. And the supercharge is generated by a Majorana fermion, I should say, just 2 real supercharges. And I also want to comment that these solutions here are localized, so around the zeros of phi. So basically, we can think of whenever phi is 0, we can think of a solution to these equations as being highly localized around some sort of 0 of phi, where in this case I'm taking to be x1 is equal to x2, 0, x3 is equal to 0. Okay, and there's a slight subtlety here, which is that technically this may not, one can argue that this may not exactly solve these equations on the nose globally on M4, but in all the examples we have, we can treat these 0 modes as extremely small masses that are way below the strong coupling scale of the gauge theory anyway. Okay, so that's the classical story. And now let's talk about reflections. So in M theory, you can canonically define reflections and time reversal, but not charge conjugation. There's no actual meaning to that a priori. Also note that the three form is a pseudo three form, or sometimes called a twisted three form, where under reflections, it goes as minus sign. So it's sort of like a magnetic field in Maxwell electromagnetism. And upon compactification on ALE space, we would seem to get a 70 superring Mills whose Bosonic content is a pseudo vector and a scalar, which is not usually what we'd expect. So how do we engineer this version? So we can do so by redefining what R1 means. So this is reflection along just the X1 coordinate, which both M theory 70 superring Mills and the 3D theory will all share. So I'm just going to be focusing on this throughout the talk. So what we can do is we could look, if we have a Lie algebra with an outer automorphism, we get a corresponding involution of this space. And this, so I'll denote this by this cal A. And this further acts on all the adjoint fields of the 70 superring Mills. So when G is equal to SUN, it just looks like this for all adjoint fields F. And then if we define R1 of 7D like this, where this is the M theory R1 composed with this operator, then we get back a 70 superring Mills with a vector and a pseudoscalar, as opposed to this more exotic looking thing. And this is relevant if you want to, for example, construct standard model type constructions where you would want a vector and a some sort of pseudoscalar. Okay, and then going from 7D to 3D, you don't necessarily need to do anything at all, anything extra. So when you compactify down, this little a will be a scalar, and this little phi will be a pseudoscalar. And technically, if we write this as the actual full scalar multiplet, this phi corresponds to a pseudoscalar multiplet. So these fermions will transform with a sign under reflection in the one direction. And just for completeness, I'm listing the gaugino here. So these signs are extremely important for the anomalies. So the anomalies I'll talk about later, they contribute with opposite signs depending on the signs of these guys. But because we want to look at anomalies that depend on localized matter, we don't want quite this R1 that I just wrote down here, because localized matter will be of this form. It'll look like the superpartners of A and phi will add together like this. And so if we employ this, then we'll get the anomaly is 0 because we get a +1 and a -1 here. So we can do a slight redefinition. I'll be a little shady on the details, but basically we compose with an orientation reversal on M4 that we sort of need to bake into the construction anyway, because if we have this orientation reversal on M4, then we can nicely guarantee that there's no Chern-Simons level shift in the massive from massive KK states, because otherwise you could break parity from this effect. But if you assume that there's an orientation reversal, then these massive KK states that we're integrating out do not shift the Chern-Simons level. You don't have to worry about it. And there's a convention such that these what I'll call chiral modes have a minus sign, and these so-called anti-chiral modes have a plus sign in this reflection. So just to briefly discuss anomalies. So the anomaly I'll focus on today is this. Is classified by this cobordism group. If you want more details, this is a nice, these are some nice papers for exposition. This one's friendlier. And so this anomaly that we're focusing on is a Z16 valued. And just to discuss what a bordism group is, it's just a classification of these four manifolds with pin plus structure modulo a cobordism. So namely M4 and this M4 and M4 prime would be in the same class in this group. And this is and furthermore, I should say that it's generated by RP4. And this, yeah, okay. So I don't think I have enough time to discuss the technicality of this slide. This is sort of just an extra sort of bit to relate this gauge parity anomaly to the G4 flux. So I should mention that more familiar to physicists is possibly the Chern-Simons level shift due to massless fermions and some real representation R. It could be a more general representation, but I'm just going to take real for now. So for example, you can't define a parity invariant n is equal to 1 super Yang-Mills theory unless you have nf is equal to nc mod 2, basically, because if you employ these shifts, then you'd get that it would be half integer under this rule.
Ethan, you've got roughly 5 more minutes.
Okay, thank you. And so what was I going to say? So this is a shift in our backgrounds earlier. We're take SUN plus 1 gauge group and switch the Higgs field off. Then we would get a Chern-Simons level shift according to which looks like this. And this nicely agrees with the, I'll be shading on the details, but this nicely agrees with the G4 flux quantization condition in M theory due to the topological properties of this P1 of X8, where X8 is given by this this quotient right here. And this is a generalization of previous work by Gukov and Sparks at this point. So let's talk about the anomaly. So if we have a Majorana fermion transforming like this in 3D, so this is a 3D Majorana fermion, and a Dirac fermion is simply just an addition of 2 Majorana fermions. You can always just think of it as just psi1 plus I psi2 of 2 Majorana fermions. Then it'll contribute to the anomaly like so. So therefore, if you have a Dirac fermion transforming like this, you'll have a -2 epsilon right here, where epsilon's a sign. So under general spin 7 compactification with this types of Higgsing, the anomaly is given by this formula, which is to repeat, should be thought of as modulo 16. So we have a factor here, which is topological, which comes from the bulk modes. And furthermore, we have contributions from the matter multiplets right here. So you have the quote unquote chiral and quote unquote anti-chiral. And R are these representations that it falls under from applying Katz-Hoffa rules here. And just to discuss a little example, is just rank 1 Higgsing. And let's say you do a bunch of connected sums of M3 times S1. Then previous studies in G2 local models count the localized 0 modes in each of these M3 times S1 factors. And then you can lift this to a spin 7 system in the approximation where these connecting tubes are thin. And then you can apply this formula. And what's nice about this formula is because, you know, the signature and Euler characteristic, you know, sum nicely, or have a composition formula nicely with connected sums. Okay, so sort of advertising this example. If you want more details, look at the paper. Then some conclusions. So we found that these spin 7 local models provide a flexible framework for engineering 3D n is equal to 1 gauge theories, modulo some subtleties on the degree in which we can trust the localized solutions. So this is, like I said, in general, there may be some sort of mass that is exponentially suppressed that's far below the strong coupling scale. And we calculated the parity anomalies of such compactifications, which is robust in the infrared. So some possible future work would be mapping at possible phases and looking at possible condensed matter applications. So namely, what sort of TQFTs or CFTs do you get under this framework? And with the addition of this possible exponentially suppressed mass that I'm talking about that deforms the CFT. You know, does this relate to the 3D duality web? Can we engineer examples of this similar to the spin 7 conifold transition? See also recent work. And yeah, it would be nice to exactly solve these spin 7 zero mode equations on the nose. We expect them to be highly metric dependent, which is unlike the G2 case, which is just purely topological. And then we're looking at possible relations to F3 and spin 7, which is due to the F theory and dark energy paper from 2018 by Heckman and collaborators. And thank you. And please let me know if you have any questions.
Let's thank Peter for giving a great talk. If you have any question, please raise your hand or just unmute yourself. It's a good question.
Yeah, Ethan, I have a question. So do you expect that in genuinely compact models, these anomalies are always absent? So in the sense that, or would these be, acceptable anomalies from a quantum gravitational perspective? Since you mentioned, right, this is a mixed anomaly in some sense involving space-time symmetry.
Yeah, so the gauge anomaly, the gauge parity anomaly, that you do expect to see even in compact solutions, and those are basically telling you that if it's non-zero, that you need to include some sort of G4 flux into the system, some half-integer G4 flux, I should say, and that will tell you that you've broken parity in the infrared. So that's actually just as true as in the non-compact case. And for the gravity parity anomalies, I would expect a similar behavior. That if you calculate this anomaly to be zero, then you would just get that your low energy theory does not conserve parity. Because in that case, with a compact spin 7, then your gravity is dynamical, and that's how I would interpret it.
I see. Okay, thank you.